Hello everyone. Today we are presenting our final project titled Where Should I Sit in Class? This project applies linear algebra concepts such as distant matrices, feature matrices, and score models to solve a very common everyday problem. We are from Group 20 and these are the members who work together on this project. Now, in this presentation, we will begin by explaining the motivation behind our project and why seat selection actually matters. After that, we will describe the data required to model the classroom mathematically. We will then introduce two different linear algebra methods used to score each seat. Finally, we will analyze the result and summarize our conclusion. So here's our introduction. Selecting a seat affects how well a student can see the board, stay comfortable, avoid noise, and access utilities. Since each student values these factors differently, choosing the best seat becomes a very personal choice. This project uses a very simple linear algebra to make that choice easier. We turn each seat's features into a list of numbers and let you rate what's most important to you. By doing a quick calculation, the method scores every seat and show you which one fits your needs best, turning a daily guess into a smart, data-driven decision. So to build our model, we first need the data. So the first data we need is the classroom layout, which is the rows and columns, and we turn it into grid representation. Second is the coordinate of every seat in rows and columns representation of X, Y. The third one is the location of important objects such as board, air conditioner, door, power outlet, and friends. And then assign preference weight, a list of score how important each factor is to the student. This is based on personal preferences. Now, there are two methods to do this. The first method is with distance-based scoring and feature matrix. And then the second one with dimensionality reduction using PCA-style feature compression. Now we now begin with method 1, which focuses on distance-based scoring and feature matrix. So the first step here is called to compute distance. The core material in this step is the Euclidean distance formula. For every seat and every important object, we'll calculate the straight line distance. In the example shown, the classroom consists of 6 seats arranged in a grid. The board is located at the center front, the air conditioner is on the left wall, and friend is sitting at seat B. Now, we calculate distances from each seat to these three objects. And now continuing the example here, we compute the exact numerical distances for all seats. For instance, we calculate how far seat A, B, and C are from the AC, the board, and the friend. We also determine the maximum distance among this value, which is later used to normalize the scores so they all lie within the same range. The second step is feature scoring. The material here is feature scoring and normalization. Raw distance cannot be compared directly, so we need to convert them into scores between 0 and 1. In the example, distance from the AC is treated as farther is better, while distance to the board and friend is treated as closer is better. Applying the formula shown, each seat receives a normalized score for each feature. Once the feature score are normalized, we go into the step 3, which is feature matrix construction. We organize them into a matrix. In this example, each row of the matrix corresponds to a seat, and each column corresponds to a feature in the order of AC, board, and friend. This feature matrix becomes the mathematical foundation for scoring all seats simultaneously. And then the final step is weighting and final scoring. The key material in this step is weighted matrix multiplication. In the example, the students assign preference weight of 40% to avoiding the AC, 30% to closeness to the port, and 30% to the closeness to a friend. Now, these values form a weight factor. By multiplying the feature matrix with this factor, we compute a single comfort score for each seat. Now, continuing the example here, we calculate the final scores for all seats and visualize them using a heat map. The highest scoring seat is identified as the best option, while the lowest score indicates at the least favorable seat. The heat map clearly highlights pattern in seating preferences across the room. So for this example here, the worst seat is going to be seat C and the best seat is going to be seat B. Now we move on to the second method using dimensionality reduction using PCA style feature compression. So the first step, we need the matrix decomposition, which we use single value decomposition. Now, in this example, we decompose the feature matrix into three matrices, which is matrix U, matrix sigma, and matrix V. Matrix U represents seat-related patterns. Matrix sigma contains singular values that indicates importance, and matrix V is the relationship between the original features. And then continuing the example here, we analyze the singular value in sigma. Larger singular value correspond to dominant factor influencing seat comfort, while smaller values represent weaker or less important effects. And then we continue it again. We remove the smallest singular value from the example. Now these steps reduce noise in the data and keep only the most significant feature combination that impacts seat quality. And then after that, we move on to the second step, which is dimensionality reduction. After removing the least significant singular value, the dimension of the matrices are reduced, resulting in a more compact representation of the seating data. Now, continuing the example here, the rows and columns corresponding to the removed singular value are automatically eliminated. This reduces the size of matrices without losing the most important seating information. Now here, we represent the final reduced dimension matrices from the example. These matrices still preserve the main seating patterns but are computationally simpler and more efficient to work with. And then after that, we move on to step 3, which is recomputing the seat score. Now using the reduced matrices, we need to recompute the seat scores. In the example, the same scoring process is applied, but now using the compressed feature representation here. And then continuing the example, we compare the new scores with the original scores from method 1. We observe that the best and worst seats remain unchanged, demonstrating that the dimensionality reduction preserved the core decision. And we still use the same method here, which is the heating map. And we can see still the worst score or the worst seat is going to be seat C, then the best seat will be seat B. So now we discuss the result. So the model here effectively translates seat feature into scores, showing that structured math can match our intuitive choice. Front seat score higher, corner score lower, and the best option becomes clear. Now, however, this is a very simplified tool. It relies on your ability to weight preference and treat real-world factors like noise as basic distances. Despite this limitation, it provides a useful data-driven way to decide where to sit. Now we get the result here. The first one is the score calculation. All seats were scored using our model, factoring in visibility, comfort, and noise. Second one is the heat map patterns. High score clustered in favorable areas, and low score appeared near doors and corners. The third one is top choice. The model identified a single best seat and several strong alternatives. Now, our conclusion of this project is that this shows how linear algebra can be used to choose the best classroom seat. By combining factors like feasibility and noise into a single score, the model clearly identifies top seat and shows that the best seat depends on a student's personal preferences. The approach is very simple, flexible, and can be adapted to other spaces like lecture halls or meeting rooms. Overall, it proves that basic math can provide practical, data-driven help with everyday decision. And on the left here is all the references that we use. That's it from our presentation. Thank you for your time and attention. We hope that this project demonstrates how mathematical tools like matrices and decomposition can help us make better and more informed decisions in daily life.